Hi, in this presentation, I'm going to walk you through Aho Corasick algorithm. The agenda for the presentation is as follows. So first I'm going to explain the problem statement. Then I will walk you through certain basic components and data structures along with their properties and certain lemmas which will be required to understand the algorithm in detail. Then I will show you the pre-computation of try data structure, failure links and output sets with time complexity analysis. Finally, we will see Aho Corasick algorithm and how it solves the problem that we have. Along with time complexity analysis. So problem statement is as follows. We are given a set of patterns P, named P1, P2, and so on Pk. So this is a set of K patterns, and we need to find all the occurrences of this set of patterns in a given text T. And the length of a pattern Pi is denoted by Mi, and the total length of patterns is given by M, and the length of the text is denoted by N. So next, let's see the difference between KMP versus Aho Corasick for this particular problem. So if we apply KMP for this problem, we need to, so we know that KMP finds all the occurrences of a single pattern in the given text. So if we apply this KMP algorithm for this multiple pattern matching, we need to first pre-process all the patterns that will take M time. Then we need to uh, run, do k passes over the text, right? So that means we will need k times n once for each pattern. So the time complexity will be k times n plus m. And then we have this Aho Corasick algorithm, which finds all the occurrence of the set of patterns in a single pass. So that means the time complexity will be something like n plus m plus z. So here we already know what n is. It is the length of the text. M is the length of the pattern. Whereas z is the total number of occurrences of the pattern in the text. Since Z is something that is related to output, so that means this algorithm is output sensitive. Then these are the basic components and data structures that we are going to look at. That is a try data structure, failure links, and output sets. So first, let's see the try data structure. So what is this try data structure for a set of strings P1, P2, and so on, Pk. In this particular problem, we have a set of patterns. So we need to build a try data structure for this set of patterns. So a try is something that is a prefix tree with the following properties. First thing is that each edge in the try is labeled exactly with one character, and from a particular node, all the edges emerging out of that particular same node must have distinct labels. And for any node V in the try, the string V star, which is formed by concatenating the edge labels from the path to the node V, along the path from the root to the node V, must be a prefix of some pattern in the set we have. Then there must exist a unique node for each pattern. That means for each string pi which belongs to P, there is exactly one node in the try such that the path from root to V spells out pi. And this particular node is labeled with index I. So these are the properties of the try data structure. Um, Then let's see how do we actually construct this try. So the first what we need to build is K1. That is K1 is nothing but the try which consists of only the first string P1. So um, it is a single path from the root where each edge is labeled with the character of P1 spelling out P1. Then let's assume we already have Ki, that means the trie for all the strings from P1 to Pi, then we need to construct Ki plus 1. That means we need to add Pi plus 1 to the existing trie. So what we can do is we can start at the root of the trie and then follow the path in Ki that matches the character of Pi plus 1. That means you start from the root, walk down along the edge labels, comparing the characters of Pi plus 1. So there can be two scenarios in this case. That is, while you're walking down, you can find the full pattern Pi plus 1. Um, in that case, you can just label the endpoint node with I plus 1. Suppose if this is not the case, that means if you encounter some mismatch along the path, then what you should do is from the point of mismatch, you will need to create a new path labeled with the remaining part of Pi plus 1, and the endpoint of that path will be labeled I plus 1. So, what will be the time complexity for this? Let's analyze. So, So first, as we can see, the time complexity for constructing Ki plus 1 from Ki is order of Mi plus 1, big O of Mi plus 1. That is the length of the pattern I plus 1. That means the overall time complexity will be M1 plus M2 plus and so on Mk. That is nothing but big O of M. M is the total length of all the patterns. So the trie data structure can be built in big O of M time, the total length of the patterns. Now let's see an example. So this is the trie data structure. So as you can see here, suppose if we want to insert something like G A C A into this particular trie, then we can start from the root here, walk down along this G matches, A matches. Then we don't have a continuation with C. That means we are finding a mismatch at this point. So from the here we can actually create the remaining path C A. And this is how the uh, construction of the trie works. I mean, I have demonstrated a single inserting a single string into a trie. So this is repeated for all the strings that you want to insert into the trie. And we have seen what will be the time complexity for this. Now let's see what a failure link is. So a failure link is something that is a pointer which will connect node a node V to node W. That means pi f of V is something is a pointer that will connect node V to node W. And here observe that V star is the concatenation of edge labels from root to node V, and pi f of V is nothing but which will have a pointer um, indicating the longest proper suffix of V star that is also a prefix of some pattern in P. That means we have node W and its concatenation of edge labels from the root labeled as W star. So here W star is the longest proper suffix of V star and it is also a prefix of some pattern in P. And pi f of V is something that is connecting node V to node W here. And see that pi f of V is the notation we use for the failure link of a node V. And V star is the path of the concatenation of path labels from root to the node V. And pi of V star is the longest proper suffix of V star that is also a prefix of a pattern in P. And also see that pi of V star, if pi of V star is an empty string, that means in that case, the failure link will be pointing back to the root itself. Then here is the example. So let me show you what a failure link is for one of this. So we have this GATA. Let's assume this is the node V. Then how do we find this failure link? So, what is the meaning of this failure link here? So, what are the prefixes of GATA? We have proper suffixes ATA, TA, and also A. These are the proper suffixes. So, do we have a prefix that means a path from the root which is labeled ATA? ATA, we don't have ATA. So ATA is not the longest proper suffix that is also a prefix of a pattern. Whereas let's see if there is TA. There is no path from the root starting TA. That means TA can also not be the longest proper suffix that is a prefix of the pattern. Whereas let's see A. A is also a proper suffix of this pattern, and we see that there is a path from the root which is starting with A. So that means A here is the longest proper suffix that is also prefix of a pattern, and in that case this will be the node W, and here this is the failure link pi f of v. So this is what a failure link means. Next, let's see. So now let's see a version of the Aho Corasick algorithm without the concept of output sets. So this version of the algorithm will work if a pattern in P, if no pattern in P is a proper substring of any other pattern in P. So without the concept of output sets, we there can be certain occurrences which will be missed by this algorithm. So let's see first what this algorithm is, then I will show you an example where it fails. That will give us an intuition of why output sets are actually required. Um, so first we initialize j to 1. This is the pointer for the text that we have. Then the pointer to the tree, which starts at root. Then what we do is we start from the root and keep matching the edge labels with the current character that we are at. So while there is an edge from V to some node V dash which is labeled T of J, then what we do is if V dash is an end of a pattern, that means if it is numbered with some I, then we know that pi occurs in t ending at position j, so we report that occurrence. Then we move from v to v dash, and then we move to the next position in the text. We increment j. So this process, this while loop, is repeated until we reach some leaf node in the trie, or we encounter some mismatch. So in those cases, this while loop will terminate, and then we see if v is equal to root, then there is the number of matched characters in the current window is 0. That means we move to the next position in the text. Otherwise, what we do smartly is we find the longest proper suffix of v that is also a prefix of the pattern, that will give us the next potential start point, right, where a pattern can occur. So that's why we traverse the failure link. So the concept is similar to the KMP algorithm, but here in this case we have multiple patterns and hence the trie data structure with failure links. And then once we traverse the failure link, again we resume the comparisons from where we have stopped earlier. So the previously matched characters are not compared again. The comparisons resume from where we have stopped before. And this whole process is repeated until um, all the text is processed, like until j is greater than n. So this algorithm seems fine, but There is some issue with this. It will not be able to report all the occurrences properly. Let's see an example where this algorithm fails to get an understanding. So, for example, in the previous example, let's say our text is GATA and CA, something like this. Then in this case, what we need to get, we need, let's see, 1, 2, 3, 4, 5, 6. Then we know that GATA is pattern P4 occurring at position 4, right? And also another thing that we will get is P1, I mean P1 that occurs at, I mean that ends at position 3. So P4 occurs in the text ending at position 4 and P1 occurs in the text ending at position 3. So these are the only occurrences of the patterns, right? So the answer should be this after running the algorithm. But what we will get, let's see. So we will start from the root, we'll compare G, A, T, A. Then we will report this. Then after that, we have nothing to go from here. So we need to traverse the failure link at this point. So we will go back here, right? And then the comparisons will resume from here, right? From to match the next part. So here we are missing AT, right? We are missing this. We are not able to report this occurrence. So this is where the algorithm fails. So in order to solve this problem, we have the concept of output sets that we are going to see next. So what is an output set? So let's say we are at the node V and we want to define what is the output of V. So from V, if we traverse a path of failure link starting from V, that means let's say from V, you took the first failure link and you reached some node W1. And from W1 again, you took a failure link W2. I mean, sorry, failure link to reach W2. And you keep on doing this until you reach the root. So you keep doing this and you will encounter some certain nodes while you're traversing these path of failure links starting from V to the root. And some nodes in this path will be numbered with some pattern numbers, right? They could be endpoints of such some pattern. So, and you collect all such pattern numbers that you encounter along the path. So, output of V is nothing but the set of all those pattern numbers. Now we see lemma 2.5.6. Let V be a node in K with V not equal to root, then U is a proper suffix of V star and a prefix of a pattern in P if and only if U is equal to pi power Q of V star. That means if you traverse a trail of failure links from V, then you will encounter some node in that path of failure links where the concatenation of edge labels from root to that particular node is U for some q greater than or equal to 1. So let's see the proof for this particular lemma. So there are two parts for this proof. The first part is that we show that pi power q v star is a proper suffix of v star and a prefix of a pattern in P. So how do we do this? So for q is equal to 1, we know this is true because pi per q of v star, if q is equal to 1, it will be pi of v star. We know that by definition of pi, pi of v star is the longest proper suffix of v star that is also a prefix of the pattern in P. Now, by inductive hypothesis, we assume that this is true for some q minus 1, that is pi per q minus 1 of v star, let it be u dash, is a proper suffix of v star and also a prefix of a pattern in P. Now, in the inductive step, we want to prove that this is true for pi per q p star. So, what we know by inductive hypothesis is that u dash is a proper suffix of v star, and we also know that pi per q v star is the longest proper suffix of u dash that is also a prefix of the pattern. That means pi per q of v star is a proper suffix of u dash. And we know u dash is a proper suffix of v star. That means pi per q of v star is a proper suffix of v star and also definitely a prefix of a pattern in P. This proves the if direction of the proof. Now, let's see the next part of the proof. So, in this part of the proof, we want to show that if U is a proper suffix of V star and a prefix of pattern in P, then U is equal to pi per Q V star for some Q greater than or equal to 1. In order to prove this, we will use proof by contradiction. So we will suppose that U is not equal to pi per Q of V star for all Q greater than or equal to 1. Then that means for some k greater than or equal to 1, we will have this inequality, right? Pi per k plus 1 of v star, the length of pi per k plus 1 of v star is less than length of u, is less than pi per k of v star, right? That means u will be some proper suffix of pi power k of v star. But according to the definition of pi, what we will have is pi per k plus 1 v star is the longest proper suffix of pi per k v star that is also a prefix of pattern in P. That is according to the definition of pi. But with this inequality, what we have is pi per k plus 1 of v star is less than the length of u, right? That is giving a contradiction to us. That means U must be pi per q of v star for some q greater than or equal to 1. So, hence proved. So, we look at lemma 2.5.7. So what this lemma says is that suppose a node V is reached in the comparison of the current character Tj with the character on the trie, uh, then pattern Pi occurs in T ending at position J if and only if I belongs to output of V. So why is this true? We will actually look at the proof for this. So the proof for this comes in two parts. So the first part says where we look at the only if direction of the proof. That means suppose Pi occurs in T ending at position J, then we need to show that I belongs to output of V. So how do we do this? So if Pi occurs in T ending at position J, then that means Pi must be a suffix of V star, right? So for suppose if Pi is equal to V star, then obviously V is labeled with number I and hence I belongs to output of V. This is true. But otherwise, if Pi is not equal to V star, then what is the case? Then according to lemma 2.5.6, then we know that for some q greater than or equal to 1, Pi is equal to pi to the power of q V star. We know this. That means we have a path of failure links V pi f of V pi square f of V to pi to the power of q f of V, that is a path of failure links from V to some node W. That node W, the concatenation of the edge labels from root to that node is W star will be equal to Pi. That means W is numbered I, right? That means obviously I belongs to output of V. So this proves the if direction of the proof. Now, Now let's see the if sorry we are looking at the we have looked at the only if direction of the proof. Now we look at the if direction of the proof, that is, if I belongs to output of v, then we show that pi is a proper suffix of v star. So how do we do this? Let I belongs to output of v, and let w be the node that is numbered with number I. So if V is equal to W, then we know that Pi occurs in T ending at position J, because V star is equal to Pi. Otherwise, if V is not equal to W, then in that case, by the definition of output of V, there is a path of failure links from V to pi f of V, pi square f of V, pi per q f of V, from V to some node W, such that pi per q f of V, so W is equal to pi per q f of V for some q greater than or equal to 1. So that means Pi is equal to W star is equal to pi per q of V star. And from lemma 2.5.6, it follows that pi per q of V star is nothing but Pi, and it will be a proper suffix of V star. So this that means Pi occurs in T ending at position J. So this proves the if direction of the proof as well. Now we are going to look at the pre-computation of failure links and output sets. So first, let's consider a node V. So if depth of V is 0 or depth of V is 1, then in that case, the failure link will point back to the root itself, right? Because they won't have any proper suffixes, right? So now let's suppose for some depth D, the failure links for all the nodes we have been calculated for every node V with depth less than or equal to D. Now the task for us is to compute the failure links for some node V such that the depth of V is D plus 1. And assume V dash is the parent of V, and the edge V dash comma V is labeled C, and we want to compute a node U, which is the node to which the failure link from V points to. So how do we do this? So let's look at the next slide, which will give us a clarity on this. So what we essentially do is, starting from V dash, we want to compute the failure link for V, and V dash is the parent of V. So we know that the depth of V dash is D, and all the nodes which come in the path of failure links from V dash will also have depth less than or equal to D. So all of them must have failure links already computed. Also notice that what could be the failure, I mean the longest proper suffix of V that is also a prefix of a pattern in P. So that could um, that means my question is, what could be pi of V star? It could be an empty string, or it could be the character C itself, or it could be some proper suffix of V dash star plus the character C. So what we can do is, we can start from V star and then traverse the trail of failure links starting from V star until the first time we encounter a node, some node wi dash in this path of failure links, which the first time until we find such a node with a continuation with the character C. And once we find that, we can just link the failure link from V to U. Suppose if we were not able to find such a node which continues with C, then in that case, what will happen in this trail of failure links? We will reach back to the root itself. Then we will see if the root has continuation C. If so, we will link the failure link. If not, if the root also does not have a failure continuation with C, then the failure link will point back to the root itself. So that is how we can compute the failure link for a particular node. Now let's see, how do we compute the output set for a node V? So we know that output of root will be 5, empty set. Next, let's assume that for some D, output of V has already been computed for all the nodes V whose depth is less than or equal to D. Now our task is to find for the nodes, output sets for the nodes with depth D plus 1. So how do we do this? So what we know is that depth of pi f of V is less than or equal to D. So that means the output of V exactly coincides with output of pi f of V, except for the case in which V is numbered 1. If V is numbered 1, you need to union I with the output of pi f of V to get the output of V, right? So that is how we can find the output set for a particular node. Uh, then let's see the algorithm for this. So whatever we have discussed now is written in the form of an algorithm. So here, we start from V dash and traverse a trail of failure links until the first time we find a node W dash, which has an emerging edge out of it, W dash comma W, which is labeled with C. In that case, we just create the failure link. Suppose if we go back to the root itself and root also does not have a continuation with C, then the failure link will point back to the root itself. Then parallelly, we do this output set finding also for a particular node. That is, if V is numbered I, then you can just union I with the output of pi f of V. If not, otherwise, output of V is exactly equal to output of pi f of V. So this is how you compute for a node V. So how do we compute the failure links and output sets for all the nodes in a particular try? You can just do a breadth first search and keep applying this algorithm 2.1.10 for each node in that breadth first search. So let's see the time complexity analysis. So one important observation that we have is that depth of pi f of v is less than or equal to depth of pi f of v dash plus 1, because v dash is a parent of v, right? So that means, what can we say about the total increase of depth over all executions of this algorithm 2.10 for the nodes on the path pi, for the nodes on the path for pattern pi? It will be definitely bounded by mi, right? It is the length of the pattern pi, because depth of pi f of v is less than or equal to depth of pi f of v dash plus 1. So that means, also another observation is that each iteration of the while loop is each iteration of the while loop is decreasing the depth of the current node by at least 1, right? Because the depth of the node to which its failure link points is strictly smaller than the depth of the node itself. This is an observation. Then um what can we say about how many times does the while loop actually execute in the entire algorithm? It can execute at most mi times, right? Because the total increase in the depth for the nodes on the path pi is bounded by mi. That means the while loop. That means the while in the while loop, you're essentially decrementing the depth. The depth is decreasing. So how many times can the while loop be executed for pattern pi? It will be at most mi times. and consequently there are at most m, I mean this is for one pattern pi, and for all the patterns the complexity will be m, right? The total length of the patterns over that will be the m executions of the while loop over the entire algorithm, and hence the worst case time complexity is order of m. So if you notice one thing, in this algorithm everything will take constant time except this while loop. So the time complexity is mainly dependent on this while loop, right? So that's why we have analyzed the time complexity with respect to that. Then now we look at the Aho Corasick algorithm. So here, first we have J, that is tracking the position in the text, and then the pointer V, that is tracking the node on the trie. At first, J is initialized with 1 and V is at root of the trie. So what we do here in the algorithm is we start from the root and we keep comparing the current character of the text along the edge labels of the trie. And so this what this while loop does is, so while there is an edge v comma v dash that is labeled tj, in that process of comparisons what we do, for each I belongs to output of v, we report that the pattern I occurs in t ending at position j. We have seen that according to lemma 2.5.7, if I belongs to output of V, then pattern I occurs in T ending at position J. So without this output set, we have seen before that certain occurrences of the patterns will be missed. In case if one pattern is a proper substring of another pattern, then we have seen an example where certain occurrences of the patterns will be missed if output sets are not used. So yeah, this is with the output sets. Then we move the v pointer to v dash and we increment the j. So this while loop continues until we reach a leaf node on the trie, or we encounter a mismatch. So in that case, what we do, we check if v is root. That means if in the current window we don't have any matched characters, then we can just increment j, move to the next character in the text. Otherwise, what we do smartly is we take the failure link of v. That means the longest proper suffix of v star, that is also a prefix of the pattern. So that will be the next potential start point for any occurrence of any pattern, right? So that's why we take the failure link. And then again the comparisons will resume from where they have stopped before. We don't match any previously matched characters again. The comparisons again start from the point where it was stopped before. So, and this process will repeat until the whole text is processed. So this is the Aho Corasick algorithm. Now let's analyze its time complexity. So the time complexity for this will be big of m plus n plus z. M is for the pre-computation of the trie failure lengths and output sets for all the patterns. Then Z is for the total number of occurrences, because we are iterating through the output set for each node in the while loop, right? So that means we need the time complexity due to that will be the total number of occurrences Z. Then this n part, how do we analyze this? Analyzing this n part is very similar to how we do the analysis in KMP algorithm. Except that KMP algorithm we have a single pattern, whereas here we have multiple patterns and hence the trie structure with failure links and output sets. So how we can think of this n part here is, we can analyze this in two ways. I will explain this in two ways. Let's first see this like two pointers thing. So we can visualize two pointers on in the text. The first pointer, let it represent the start point of the current window of matching. Then let j track the end point of the current window of matching. Okay, so as we see, this j moves as we make the comparisons with the edge labels on the drive. So we keep moving this. So Uh, when a mismatch or occurs, or when you reach the leaf node on a try, you try to take a failure link, right? When you take a failure link, essentially the start point of the current window moves to the right side. So that means these two pointers can only move to the right side. They never move back. So that means what will the time complexity be? N plus n, right? So that means it will be big O of n. Also, put in other words, we can, if we try to analyze it in terms of the number of character matches and mismatches, in that case also, if you see, an already matched character is never matched again. The comparisons resume from where they have stopped before. That means there can be at most n character matches. And how many mismatches can occur? So, per possible start point, there can be at most one mismatch, right? So that means, and the possible start points are n. So that means there can be at most n character mismatches, or so it can either be a mismatch, or you can reach a leaf node on a try. So whatever that is, you take a failure link in that case. So that means there can be n character matches and n character mismatches. In that, even if you think in that way, it will be big O of n. So that means the overall complexity will be big O of m plus n plus z. Since we already have the try data structure with failure links and output sets pre-processed before, taking any failure link will take constant time. So this is the Aho Corasick algorithm, and these are the references, and thank you.